Hi, good morning everyone. Welcome to my talk. But first of all, let me begin by thanking the organizers of this special symposium between European Ceramic Society and the American Ceramic Society, Dr. Tatsuki Oji, Dr. John Binner, Dr. Martha McCartney, and Dr. Anne Lerich for their kind invitation to allow us to present our work at this symposium. My group has been working for quite some time on the chemically processed functional ceramics. So basically what we are doing is to start with molecular precursors and then processing them in either solution-based techniques or gas-phase methods to make nanopowders and thin films. And today I would like to share the general concept of this chemically derived materials processing and also give you two examples for application of nanoparticles in health, for biodiagnostics, and also for energy requirements. So how you can use these materials for energy storage or for production of molecules which can be used as an energy carrier. So here we see an example of a simple titanium alkoxide which has been processed by solution-based synthesis, a sol-gel technique to make nanopowder. Now we go a step further and we use these powders and modify them on the surface by using organic ligands with certain functional group which can chelate on the surface, so there is a real chemical bonding. And this conjugation of organic molecules on the nanoparticles or on solid surface allows us to change their fundamental properties. Like typically these inorganic ceramic powders are sedimenting in solution, they are not very stable. But by having the right surface chemistry, we can disperse them very well and can create a translucent or a stable dispersion, as you see here on the right side, where we have a comparison between a non-functionalized and functionalized nanoparticle. And these dispersions can be used for different kind of application, like for printing. So on the left-hand side of the slide, you see gas sensor which have been printed based on water-based tin oxide functional ink. On the right side, we have a piezoelectric material, potassium sodium niobate, which has been also deposited by sol-gel method for making different piezo transducers. So in a generic way, what we are doing is we are looking at the library of molecular precursors, and then based on their properties, if they have a high vapor pressure, that means if they fly in the gas phase, can provide appropriate feedstock, then they are used in gas phase techniques like this example shown here on this slide of a plasma enhanced CVD, where we can use the kinetic energy of electrons to split some of the chemical bonds in these metal organic compounds and then have deposition of functional ceramic coatings on different substrates at low temperatures. The same chemistry can be used to detect or identify certain breaking points where we have, for example, a preferential hydrolysis in the molecule to create an unsaturated metal coordination. So it promotes the molecular precursor, which is now partially hydrolyzed, to undergo cross-condensation reaction, and this leads to the nucleation process, which is chemically controlled, something which is very well known for the sol-gel processing of nanopowders. Here we see an example of an atomic layer deposition where we have used different kind of precursors, well-defined molecular precursors, to do fine coatings, nanoscopic coatings of ceramics or metals in trenches. So on the right side, on the right-hand end of this slide, you see a transparent coating of copper on glass. And this is so thin, but it still has the metallic conductivity, and this can be used because of its very thin nature. It is not peeling apart when the substrate is being bent. So it is very good for organic electronics or for transparent electronics or for stretchables. And these kind of processing where you are having a materials economy focus is very advantageous when we are using the metal organic compounds or molecular precursors. Another attribute of these precursors is that we can very nicely tune the phase boundaries, in the sense that by using different molecular precursor or building blocks, we can deposit different compounds under similar condition. So here's an example of a titanium building block which has been modified to deposit amorphous titania, anatase or rutile, just by changing one of the ligands around titanium. So this gives us an enormous flexibility when it comes to processing. So by changing the chemical input, we can then finally decide the output, which is shown on this slide. Another advantage of using molecular precursor is that when we are nucleating a solid from solution, we can control these processes by the concentration and by keeping the time of nucleation very slow. So if you have a very high reactive precursor, then the nucleation time, the condensation reactions are running so fast that you have a nucleation burst. And this has been shown for a lot of compounds, especially metals, but in oxides, this is very important to have, because otherwise you have an agglomerate at the end. And if we control the nucleation phase, then we have very well-defined powders. As you see on the next slide, this is a well-known example of sand, which is insoluble in macroscopic form, but as you reduce the size of the crystallites, you make it soluble, more soluble, and in nanoscopic form, nanosilica particles are almost soluble, and then in fact degrade over a certain period of time in water and by forming silicic acid. That's one of the reasons that silica nanoparticles have been used for a lot of biomedical applications. So once we have these solutions, they can be now used for different applications like spraying. So we can use an ultrasonic spray nozzle and use this solution to make a coating by spraying. And this is an example of an anti-reflective coating on glass where we have used titanium and silica particles to make a very homogeneous coating on or bilayers on these glass substrates. Another example is of the surface functionality is by attaching highly fluorinated organic molecules like the one shown here. This is a polymer which is having a lot of fluorine units in the backbone, and it is highly thermally stable. And there is a current need of hydrophobic surfaces which are stable at high temperature. And by linking or coupling these organic molecules to an inorganic carrier like the spinel particle shown here, we were able to demonstrate that the hydrophobicity is maintained up to 300 degrees C. And so far, there is no example. There is only up to 200 degrees centigrade, you have hydrophobic surfaces which are stable. After that, the hydrophobicity is lost because the organic compound, which is immobilized on the surface and is responsible for the hydrophobicity, it starts decomposing. So basically, you are left with a bare ceramic surface. And in our case, we have these particles are covalently attached and they remain associated till 300 degrees C. This work has just appeared in Advanced Engineering Materials in 2020. So this combination of surface roughness and chemical topography is something that is allowing us also to design not only ultra-hydrophobic, but also isophobic coatings. Now, this is the background that we are coming from, but I would like to now use the rest of the time for two special applications that was also in the title of my abstract. So one is the use of nanoparticles as carriers of functionality to perform on-surface chemistry, which can be used for health applications. So in Cologne, we have a focus on making these nanoparticles as nanoprobes for transmitting or for transferring them across the biological barriers. So this can be done by attaching the right groups. For example, if the cell-penetrating peptides are attached on these inorganic carriers, this particle, which is now more like a bioconjugate of an inorganic carrier fused with a functional organic molecule, it can easily pass through the biological barriers. Like, for example, this epithelial barrier, a biological membrane. And this can be done by attaching different kind of biological molecules like RNA, peptides or antibodies, and even radionuclides to make these conjugates. So here is an example of iron oxide particles. An iron oxide can be made in these cubic shape, as you see on the right side in the TM image. And since iron oxide has a lot of hydroxyl groups and it's a basic oxide, it's very easy to condense it with the silicic acid. So it's a simple Lewis acid-base condensation, which gives now a nanoparticle which is completely encapsulated with silicon oxide. And these silicon oxide shells, they have hydroxyl groups which can again be used to do certain chemistry or to hook an organic molecule like folic acid. So this was done by first functionalizing the silica surface with an aminosilane, and this amino group then now can be condensed with the carboxylic group of a drug, for example, for folic acid, and it can be an antibiotic drug like ciprofloxacin, but the example you see here on this slide is of folic acid. Now, if this particle, this conjugate, is brought next to the cell, which is having a lot of folate receptors, then this particle, because of the surface decoration with folic acid, will be preferentially taken up. And this was shown in the PhD thesis of Laura Wortmann, who is here on the slide. And she could show that when compared to the uncoated particles, the particles having this folic acid coating, they have a much higher uptake. And the localization around the tumor was much higher because of the surface-specific interaction with the tumor cells, which have a very high uptake of ingredients or nutrients. And that's why these particles with this right surface functionality are taken up. And based on this understanding, now we are developing different kind of protocols. So here is another example of a copper catalyzed acid alkyne cycloaddition carbodiamide cross-linker coupling, or a retro-Diels-Elder reaction. So what is common in this slide is the approach of having a covalent chemistry between two different kinds of particles. So sometimes it is very challenging to bring two different functionalities on a single nanoparticle. And we have figured out that it is simpler if we have two nanoparticles with two functionalities and they are chemically clubbed. So what you see here with these different kind of link chemistry is the possibility of covalently bringing these two particles, unifying them in a particle aggregate, and also then functionalizing them in a way that they can also be detached. So the retro-Diels-Elder reaction on the right side shows that these particles at higher temperature, when you go up more than 50, 60, they can be detached again. That means the particle can do the work, and by a certain stimulus, it can also be then separated from the cargo can be separated from the carrier. And here's an example which was used for of these to detect microRNA, which are very important biological marker molecules. And the problem with detection of RNA is that they are not very, so they are short-lived, and their lifetime in the body fluid is not very high, and they are prone to quick renal filtration. But if we have nanoparticles which can go inside the cells and detect these molecules, which are a very good diagnostic marker for certain diseases, then we can go for an early detection of the diseases. And this was done in a PhD thesis of Dr. Isabel Gessner. This is the report showing here that where we have captured and purified microRNA 198, which is a well-known tumor suppressor. So by taking a nanoparticle which was having a complementary strand, and it was introduced into the cell, which then hybridized. And after the hybridization within the cell, the nanoparticle was taken out of the cell by magnetic filtration. And by digesting this nanoparticle and doing analysis of the proteins, and we could figure out that we can selectively capture these RNA which are present in the cell by using these nanoparticles carrying the complementary single-stranded RNA. Now the goal moving forward is to have bifunctional, these kind of dual imaging probe nanoparticles having on one side a vector molecule which tells where to go and how to attach to for example, to the tumor, and then a functionality which can be used either to image or to treat so it can be a therapeutic functionality, like if you have a radioactive nuclide which can decompose or which can decay and emit radiation that can kill the tumor, or we can have the possibility of an optical unit which can be used for sensing or for imaging the tumor. And this has been realized by combining these, as you see here on the iron oxide nanoparticle. On one side we have a group, a functional ligand with amino functionality, which can then be used, for example, for coupling chelate, which like the DOTA, which is good for coordinating radioactive nuclide like 68 gallium or 117 lutetium. Or on the right side, we have a group with an azide unit on the outside of the nanoparticle, and this can be used for an azide-alkyl coupling, a cyclo addition, a dipolar cycloaddition, and this click chemistry, because it happens very quick, that's the name, that it clicks because of the compatibility of these two groups. and then you have a covalent attachment due to the formation of this 5-member ring shown in the blue box. And this has been used for a lot of application, and here are some of the publication, because this allows us to combine, for example, radioactive nuclides with a drug or other biological molecule which will have a preferential attachment to the tumor. So these kind of dual functional nanobioconjugates have in the center a ceramic particle which has now a Janus-headed surface chemistry. On one side, we have a ligand, a target ligand, which will go and address the receptor of the cell, and on the right side, we have a functionality which is either good for imaging or for a therapeutic application. So I think with this, I move to the second example that's most related to the energy, and this is about the photoelectrochemical splitting of water to create hydrogen. We have been working in this area for quite some time, and there is a huge need for hydrogen as a green energy source, or also as a storable energy source, and there is a huge market, 150 billion. It is estimated to be $100 billion US. And right now there are several methods. It can be done by electrolysis. It can be hydrogen can be created by fermentation methods, by using microorganisms, and mostly the hydrogen that is being used now is being produced by petrochemicals. So by petrochemical industries, which is actually during the cracking process, you have a lot of hydrogen being produced. Now, these are all fossil sources, and in an effort to decarbonize the economy, people are looking for hydrogen production with carbon-free sources. And water, or especially the saline water, seawater, is a very abundant source to create hydrogen by splitting water. Now, and water splitting reaction is very well known in the nature, mostly done by photosynthesis. Now, if it is done by artificial photosynthesis, we need a medium which is allowing us to have a very or quicker electron transport than what we see in the biomass, where the nature is using these photo systems 1 and 2 to harvest the sun energy and to create electrons, which are used, for example, to convert carbon dioxide and water in carbohydrate. So the hydrogen there is stored in form of sugar. But if you really want to have hydrogen like we do in the commercial electrolyzer by photoelectrochemistry, then we need the right materials. So it's not only the question of the scale, it's also the question of the cost. So the reaction is feasible. This we know that we just need 1.23 volt theoretically to split water. But if we want to scale it up, like here's on the right side an example, if you want to make a panel with 10% efficiency and an area of 10,000 square kilometer, this will be costing us more than $200 billion US only for devices. And then for storage and dispensing. So this is also an important factor to consider, to use materials which are earth abundant and economically available. So if you look at the challenge of green hydrogen for decarbonization of economy, we see it on this slide. So on the left side, we have the commercial electrolyzer of the company Siemens, and this is optimized. You see, this can run and produce the hydrogen. As you see, the cost 50 kilowatt is the energy that is needed to produce 1 kilogram of hydrogen. And right now we are around 4 to 5 euros per kilogram of hydrogen. By photoelectrolysis, the desired cost is to bring it to the same level or even lesser. So these are some of the targets given by the Department of Energy, DOE. And here the idea is to use completely bias-free. That means you take a photoactive material, immerse it in the water, which should have the right electrolyte, and then this semiconductor should harvest sun or solar energy and then perform the water splitting reaction. So the reaction is very simple, but then obviously there are boundary conditions. For example, we need a good solar to hydrogen efficiency. That means the stability of this material, the semiconductor material, which is the solar harvester, the photoabsorber, it should be stable in a wide range of pH. and it should be at least stable for 6 months. Then it should have a cost-effective processing. A lot of semiconductors which have been shown to be effective, they are very expensive. So we have to look at materials which are easy to make and also easy to recycle. So cost effectiveness is an important parameter, and then the scalability. So if you use like the platinum group metals, for example, then we know that scaling them up will be a challenge. And on the right hand side, we see the fundamental factors. So for getting a high photocurrent, we need to optimize 3 factors. One is the absorption cross-section. That means the amount of photons being harvested by a material. Then the efficiency of charge separation. So once the photons are absorbed and you have the charge carriers being produced, they should be separated, and these should be very well taken to the counter electrode. And finally, the catalytic efficiency of the surface, because the reduction and oxidation reaction are happening on the surface. So the reduction of protons and the oxidation of hydroxyl radicals, it's happening on the surface of the electrodes. So there are fundamental limitations in terms of when we look at the water splitting reaction. I'm not going into all the details, but the message here is that we have to strike a balance between the photophysical processes, that means the charge creation, so photon absorption of photons, charge separation, and their transport when they are transported within the system, and then their use to run these chemical reactions. And we have here 2 reactions: the 2-electron process to produce hydrogen and the 4-electron process to create oxygen. And that's the 2 complementary reactions, OER and HER, oxygen evolution and hydrogen evolution reaction. And for this, we need to match both absorption and incident photon to photon conversion efficiency. And that's why a large number of materials have been tested. And typically, the criteria is that the suitable semiconductor material must have a conduction band energy which is higher than the reduction potential of water. That means when you are looking at H2H plus pair, and the valence band energy should be lower than the oxidation potential of water. That means when you are oxidizing the OH radical or hydroxyl ions. So a lot of materials, as I said, that there are 3,5 semiconductors which have been tested. Metal oxynitride, so the 3,5 semiconductors have the issues with the cost. They are effective, and and bias-free water splitting has been performed, but it is due to the high cost that they are not being implemented in large area. Metal oxynitrides are interesting because they allow, by an incorporation of nitrogen, we can tune the band gap, also in combination with the different metals like mixed metal nitrides. But here also the stability of these materials in different pH ranges is an issue. Same is with metal chalcogenide. The selenides and sulfides are also very interesting, but these compounds are also having the problem of of the stability, because slowly they get transformed into oxysulfide, oxysenilides, which changes the electronic structure and also the properties of the material. The metal oxides are stable, and most of the metal oxides are stable, for example, in the pH range which is needed, but they have intrinsic problem of low electronic conductivity. And this is something which is being optimized by adding dopants or by different other techniques. So one example which is very well known is the iron oxide hematite. And in this search for photocatalysts with enhanced stability and photoabsorption, there is a huge focus on metal oxide which are absorbing in the region where you have highest number of photons coming from the sun. So we all know that titanium oxide is a very good photoabsorber, but it has a very large band gap, so only UV photons are being absorbed. But if we take hematite, here the band gap is around 2.1 electron volt, so it is absorbing a lot of visible light. And if this visible light activity can be converted into a photoelectrochemical activity, this could be a very interesting material for producing hydrogen from water. But as I just mentioned, there are limitations in terms of the lifetime of charge carriers is only few picoseconds, and the diffusion length. So you can't make iron oxide photocatalyst films or powders very thick, because the charge carriers, the photo-generated charge carriers, can only diffuse up to a few nanometers, and otherwise they will recombine. So this is the challenge when it comes to design these electrode materials. But still, iron oxide is one of the most investigated material. As you see here on this slide, more than 80% of the published data is on iron oxide. And there have been very nice reports showing how the photoelectrochemical efficiency of hematite can be improved by using different techniques of processing, or using this material in combination with other photoabsorber or photocatalyst. So what we have done in Cologne is we have used our molecular-based synthesis of hematite. So here you see an iron alkoxide, which was used in plasma-enhanced CVD to make hematite films, also at large scale. And here you see on the right side 2 films of different thicknesses. The thicker hematite film has the typical rust color that we know from the bulk rust, but this is not good due to the very fast recombination. The optimal thickness of hematite is shown on the lower side in this film, which is almost transparent, but here between 300 to 500 nanometer, we have the right material for performing the water splitting reaction. So right now, and we have scaled it up, we have made some PEC module, as you see on the lower end of this slide, but the challenge of photocatalysts with high durability and high surface activity is still there. So because after some time, the surface is either poisoned or there are other surface groups, so that the reactivity, and it can also be other phenomena like gas bubble formation on the surface, which is leading to the fact that you don't have a very high surface reactivity. So we need new processing and modification concepts for old materials. And I would like to very briefly in the next few minutes show you 2 approaches that we are following in Cologne. One is to create crystalline and amorphous junction. Here the idea is to take a material and structure it, for example with femtosecond laser, and create amorphous crystalline boundaries. So we have the same material which is compositionally homogeneous. So if it is titanium oxide, it's completely titanium oxide, but we have a crystallographic heterogeneity. That means certain domains are crystalline, the others are amorphous. And these kind of heterostructures have shown to be very interesting to modulate the electronic structure and also to have a high catalytic activity. This we have published also in collaboration with Dr. Choi, who is looking at the DFT part of this work, that how the band alignment of amorphous crystalline material, the same chemical composition based on the ordering of these 2 phases, where on one side the disordered amorphous material and the other side with the long range ordering, how the electronic structure is changing at the interface. So this is the experimental map of doing this. So we are using the amorphous films that we are obtaining by plasma enhanced CVD. These are structured by using femtosecond lasers. And by shining femtosecond laser, we can create domains or stripes of these crystalline phases, which are adjacent to the amorphous material with the same composition. And this gives us an optimal composition of high light absorption with high catalytic activity. And using these kind of films, we have been able to make photoelectrochemical cells with high photocurrent, as you see here in a typical example on this slide. But still, we need to have these on large scale areas. The photo conductors that we are processing using femtosecond, these are small 1 square centimeter substrate. And that's why scaling it at high or in large area is still a challenge for us. The second approach that we have also observed in our last few years of research is that the anisotropy of the grains. If we have nanowires or elongated grains, then the charge transport is more efficient when compared to an isotropic grain or equix grain. So for this, we have recently started performing CVD in external magnetic field. And this is very interesting that the application of external magnetic field has a very striking effect on the texture of the film, so the grain orientation. And here's one example that we can change the surface morphology and the grain orientation by applying small amount of field. So on the left side, on the left top, you see the magnetite film, for example, which is without field, and then the field assisted. And if we compare the X-ray diffraction profile, we see that certain peaks are prominent because of this texturing of these grains in these films. So by applying magnetic field of different strength, we can tune in this cross-sectional image, you see that these grains are having an elongation. So this anisotropy is leading to a high conductivity. And we have done this on different kind of substrate. And here is an example of glass substrate where we have performed the PECVD of hematite under external applied magnetic field. And this has led to a high photocurrent, as we see on the next slide, that by creating rod-like hematite structure with 110 facets that are exposed to the electrolyte, we have a much higher photocurrent. And this was done on a very small substrate, so the overall photocurrent value is small. But on the whole, this is a very promising approach because we are using the same material. Just by changing the processing condition, we have a very high activity. So almost double the photocurrent just by applying magnetic field, which is orienting all the magnetic grains in a certain direction. So with this, I would like to come to the end. And in summary, what I've been able to show you that there is a comprehensive photocatalyst database available for creating or for splitting water to create solar hydrogen. We need a deeper insight into reaction mechanism, and this is being done by ab initio or operando spectroscopy, also in our group. And we have to move from the efficiency that we achieve on the lab size sample to a larger sample in order to have a cost competitive hydrogen production. And then there are other issues that we have also observed when we have performed long time studies by operating a PEC cell for several weeks. Technical issues like the pH gradients, because both the gases are soluble in water, so there is a pH drift. And then the scalability and safety, because when you have a large amount of both oxygen and hydrogen being produced in one vessel or in one reactor, you have oxy-fuel there. So we need to have these in different compartments. And then finally, the new approaches like the tandem approaches of combining photovoltaic cells or having a tandem setup where on a photovoltaic cell, silicon-based, on one side we have the photoabsorber, photocatalyst, and on the other side the photovoltaic element. These kind of tandem units can also enhance this efficiency. I would not like to finish before thanking my co-workers for doing this work and also for the funding agencies for funding our research. And with this, I would like to thank you all, and I'm available. I know there is a live session now for any kind of questions. Thank you.